So thank you, Tom. My name is Michael Worcester, and I'm a driver engineer from Imagination Technologies, so we make mobile IP. And today I'm going to be talking about when you should be using Vulkan, when you should start to use Vulkan, and when you should continue to use Vulkan, and why you should do that. So in a perfect world, my presentation will be extremely short, just this slide. So when you should use Vulkan, all the time. Why? It's pretty bloody dope. It's the best API out there, but we don't live in a perfect world. So let's go through a few situations where perhaps you can't use Vulkan, or more importantly, you can't use Vulkan exclusively. So first of all, platform support. Tom's mentioned this already. We have large amounts of platform support. But at the same time, there are still platforms you can't run Vulkan on. So Vulkan requires roughly OpenGL 3.1 hardware support. And there's still a huge number of mobile devices, at least out there, that just don't have that hardware support. And you won't be seeing Vulkan on that probably ever. There are some devices which might be technically capable of supporting it, but for whatever reason aren't going to receive those updates. And again, these are platforms you can't target with Vulkan. And of course, there's all those platforms which are receiving driver updates and could run Vulkan, but won't. For example, consoles. So this is a problem of time. Vulkan's 50% market share on desktop, getting there on mobile, and every day, more and more devices are coming out with Vulkan. But today, if you want to target a bigger portion of the devices that you want to target, you're going to have to use Vulkan plus something else. Vulkan's a year old, and as an implementer, I write drivers, and I'm pitting about 2 years of my code against 20 years of an OpenGL implementation, which isn't a very fair comparison. So the drivers are, at this age, significantly better than any other driver we've ever put out in the past, but they're still very young. There's still large amounts of work that can be done on the drivers. The same is true of the tools and ecosystem. So we're going to be hearing from some of the LunarG guys about the validation layers, the loader, and they're improving day by day, and the rate at which they're improving is increasing. But there are still gaps, which means if you compare the tools and ecosystem between Vulkan and one of the more traditional APIs, Vulkan still falls a little short. And the same is true of third-party library, middleware. I can go and type into Google or Bing, whatever your favorite search engine is, I want a font rendering library for OpenGL, and you're probably going to get quite a few hits. For Vulkan, not so true. And again, this is a question of time. Either you can wait for all these things to mature, or you can invest your own developer time into it. And finally, this isn't really touched on too much. So even if you have a platform which is technically capable of running Vulkan, and you've decided to invest all the time into actually writing the tools, working around the ecosystem holes, it's still a different set of skills than OpenGL or Direct3D. So it's not a completely different set of skills. You certainly don't have to throw all the knowledge you've spent the last 20 years learning, but there's certainly more knowledge you need to effectively use Vulkan. And this is because OpenGL, Direct3D, as Tom said, we hide a huge amount of the hardware complexity. We hide it from you so that you can make mistakes, and even making those mistakes, your applications will still run pretty well. We go to huge amounts of effort in the driver to make sure that that happens, and in Vulkan we don't. We've thrown up our hands and said, enough is enough. More importantly, you told us enough is enough. You want to take control of your application, and you want us to stop hiding CPU work. So to effectively use Vulkan, if you make those same mistakes, your application will either not run at all, or it will run worse than it would have run in OpenGL. So to effectively use Vulkan, as application developers, you really need a much more in-depth knowledge of exactly what the GPU is doing at an architecture level. And again, it's a question of time that you need to invest into learning these new skills. But perhaps, after a couple of beers at the pub, if you tilt your head and squint your eyes a little bit, you can possibly view these past 3 points as not negatives at all, but positives going forwards. So if we look at platform support, sure, we're at 50% of desktop market, we're ever increasing in mobile, but OpenGL's not getting any bigger either. Direct3D's not getting any bigger. The platform which is getting the most support going forwards is Vulkan. Vulkan is the future. And it's not just in terms of platform support, it's also in terms of effort. So while it's certainly untrue to say that OpenGL or OpenGL are in maintenance mode or abandoned, that's not true at all. But as Khronos and as implementers, we're putting a lot more of our focus into doing Vulkan. So if you want to get on the latest trends in hardware design, in new features, in new extensions, it's much more likely that those are going to appear in Vulkan before, if ever, they appear in the other APIs. On maturity, as an implementer when writing the driver, certainly one of the best parts about writing a Vulkan implementation was the fact that I could, with the benefit of 20 years of OpenGL development hindsight, look back and take all the best parts of our OpenGL implementations. But then I could also look back and identify parts of the application that are legacy cruft. Indeed, some parts of the drivers that are there simply to make applications that might not even exist work better. Whereas in Vulkan, we're already saying it's the application's responsibility to do this. So we can just tear out large parts of the implementation. And it's also true of the application. It's entirely likely that within your engines, within your code, you've got chunks of code that are designed to work around weird implementation issues. And on Vulkan, those may no longer exist. So starting a Vulkan application is a chance to clean house. And I'm not saying throw everything away, but partially. And for skills, an investment in skills into Vulkan is not just for Vulkan. All of the modern APIs require the same set of skills. And indeed, the skills you will learn for Vulkan could make your OpenGL and OpenGLES applications better as well, because fundamentally they're still running on the same pieces of hardware, and it might help to understand the places where the implementation is taking your hand. So it's all about time. And if you can invest for time, then the rewards are great. And what are the rewards? Well, fundamentally, it's about performance. And Cort and I think Alon are going to be giving exact case studies, so I'm going to talk in the abstract. Vulkan is about performance, and we can break performance down into about 3 different areas. The first is efficiency, and by that I mean single-threaded performance. Clock for clock, using Vulkan, you can get more done. Or for me, perhaps more importantly, percentage drop in battery life for percentage drop in battery life. With Vulkan, you can get more done. And of course, Vulkan wouldn't be Vulkan without the multi-threaded story. OEMs and SOC vendors are actually going insane. You can get mobile phones with 10 cores, and if we're not going to use those 10 cores, then who is? Finally, some GPU efficiency gains, but we'll talk about that later. So let's talk about how do we get these single-threaded efficiency gains, and how do we get these multi-threaded efficiency gains? So probably the primary way in which we gain efficiency using OpenGL is through command buffers. So what is a command buffer? A command buffer is just a buffer into which you can record commands, and that's it. You don't do anything with those command buffers during recording. At some point later, you can take your command buffer and submit it to the GPU, and then the GPU will execute those commands. But these are 2 completely separated concepts. In OpenGL, that's untrue, so modular display lists, which we don't talk about. The problem with the driver, the problem with OpenGL is the fact that it's an immediate mode API means from the point of view of a driver, an application says, do a draw call, do a draw call, do a draw call. And the driver's sitting there going, okay, how many more is going to come? And it has no idea. So the application might send 1 more draw call, in which case it's probably beneficial for the driver to sit there, accept the next draw call, and then send it to the GPU. But if the application is going to send 1,000, 100,000 more draw calls, the driver's going to have to buffer up some amount. And how much is it going to buffer up? Probably taking a best case guess. And the problem with that is it's a heuristic, and it might work well for some applications, but it might work worse for other applications. And that's what Vulkan is trying to avoid. It's trying to avoid the driver having to guess what the application means. Instead, the application tells us what it means. So the other nice thing about command buffers is because you know how much work is going to be up front, you're not going to get hitching. You're not going to see the driver start to go hiccup, hiccup, hiccup when you start sending certain granularities of work. Now, in order to get multi-threaded efficiency, we first of all have to take a step back and look at how OpenGL differs from Vulkan. So in OpenGL, it's immediate mode, and it's also global. So you say do a draw call, and you say do a draw call to OpenGL, whatever that means. In Vulkan, no. You say do a draw call to a specific command buffer, or do a dispatch to a specific command buffer. So command buffers are owned by a command pool, and command pools are great. They're one of the kind of weirder parts of Vulkan. But what command buffers allow the implementation to do is amortize the cost of resource allocation across multiple command buffers. And they also provide the synchronization point. So while you can go multi-threaded across command buffers, you can't go multi-threaded across an individual command pool. So effectively what you're probably going to see is allocating a command pool per thread, tying it to that thread and ensuring that each thread has its own context onto which it can record commands. There are two flavors of command pool, and we'll talk about why this is important later, but you can either make a command pool where each command buffer you allocate from that pool can be reset individually, can be worked with individually, or probably more the traditional way of working where you can take the command pool, allocate a whole bunch of command buffers from it, and then blat those command buffers back in one fell swoop, which is probably how we're going to work today. At the start of our frame, we're going to say, let's start recording work. Record, submit, next frame, reclaim all the resources. And we'll see why there's other ways of doing that which can be more efficient in a little bit. So this is just an awful example of OpenGL, single-threaded, bad, Vulkan, 10 threads, wide and deep, good. So what can we actually put inside a command buffer? Well, in OpenGL, there's dispatch commands, and there's drawing commands, and there's a few other miscellaneous commands. In Vulkan, largely, most commands can be broken down into transfer, graphics, compute, or synchronization. So let's quickly go through what those mean. Transfer commands are raw copies with some changes. They're not exactly raw copies. You can do things like changing the tiling of an image. And it's important to note that that's the only way you can change the tiling of an image, which is important for GPU to CPU readback. So obviously, there's a few different directions you can transfer data on. So why would you want to do that? Well, in OpenGL, we did a lot of staging for you, and you'll see in the modern APIs, this concept has been completely removed. It's now entirely the application's job. So if you have a buffer on the CPU and you want to make it available on the GPU in card local memory, which isn't CPU accessible, you're going to have to schedule an upload to take it from the CPU and put it onto the GPU. And also, because of tiling, you'll need to do this even on something like a UMA system. And the opposite direction is exactly the same. If you've generated data on the GPU and you want to read it back on the CPU, you'll have to schedule a transfer to pull it back across from the GPU to the CPU. But there's also cases you might want to do a GPU to GPU transfer, and two reasons for that. In OpenGL, it's very difficult to schedule work to happen on the GPU timeline because everything's synchronized, everything's serial in OpenGL. CPU and GPU timelines are almost the same thing. Because we embrace the asynchronousness of GPUs in Vulkan, we also need to provide a way for you to schedule work to happen on the GPU timeline rather than the CPU timeline. So a really basic example would be if you submit a command buffer and then you want to submit the same command buffer again, but update the uniforms for that command buffer, what you might do is schedule a transfer between those two command buffer executions that update the uniforms. And of course, there are other uses for it like blitz, filters, and the most simple case, mipgen. So command buffers have another kind of weirdism to them where if you read through the spec or the reference card, you'll see a bunch of attributes which say this command can be used inside or outside a render pass. So I don't quite have enough time to go through exactly what render passes are, but suffice to say, it's another way for the application to provide way more information up front. So the implementation doesn't have to guess. We don't have to guess, oh, are you finished with your graphics work? Should we flush the hardware? Are you just doing a single dispatch before doing more graphics work? No, it's the application's job to say, this is the start of my rendering, here's a bunch of commands, this is the end of my rendering. And in order to ensure that the implementation doesn't have to guess, we have a limitation that a render pass has to be entirely within one command buffer. So this is just a blow-up of saying you've got a dispatch, then you're binding a bunch of state, beginning your render pass, and you're going to submit a whole bunch of draw calls. But this poses a problem. If a render pass has to be entirely within a single command buffer, how do we go multi-threaded? Because to go multi-threaded, we need multiple command buffers. Well, we solve this by the concept of secondary command buffers. So there is really no difference between a primary command buffer and a secondary command buffer, other than a secondary command buffer gets executed by a primary command buffer rather than directly by the GPU, and a primary command buffer cannot be called from within another primary command buffer. So what we can do is we can go wide within our rendering commands. We can spawn 10 different command buffers, chop our scene into 10 different parts, record our scene on 10 different threads, and then stitch them back together in the execute commands. And execute commands is extremely lightweight compared to actually doing the recording of the commands. On some implementations, it can be as much as a pointer write. On others, it might be a little bit more, but it's infinitely faster than re-recording the commands directly into the primary command buffer. So with these secondary command buffers, like I said before, there are some cases where you don't just re-record your entire draw calls every single frame. So let's look at an example of that. So there is a demo called GNOME Horde, which I don't think I have with me. and this is taken from that demo. So in GNOME Horde, what we do is we split the scene into a whole bunch of rectangular or square regions, viewed from above. It's a 2D scene-ish. We point the camera at it, we do some frustum culling, and we decide which tiles, which regions of the scene are in view. So that's all the green squares here. We then, for each particular region, go record a command buffer. And it's a little bit more complicated than just recording a command buffer. Regions which are very far away from the camera, will record at a lower LOD. Regions which are closer will record at a higher LOD. And then we submit that to the GPU, jobs are good. So next frame, the camera is going to move. And what we could do is we could reset all of those command buffers and we could re-record the entire scene from scratch, which is what you have to do in OpenGL. It's what you have to do in Direct 3D. But it's wasteful because the vast majority of the commands you recorded the previous frame are exactly the same as the commands you're going to record this frame. So if you'll excuse my awful colors, I'm colorblind, the camera's swept up a little bit to the left. The red squares are squares which used to be in view the previous frame and are no longer in view this frame. So this is a case where we're going to individually reset the command buffer that corresponds to that scene, or that part of the scene. So we're going to reclaim the resources. We don't want them to just build up and build up. So we'll reclaim them now. And we've got some new scenes, new tiles which have come into view. So we're going to record some new command buffers here. And what's interesting is we've seen in a perfect micro benchmark, you're re-recording maybe 10% of the scene every frame, which means 90% of the CPU work is not cheap, it's not Vulkan efficient, it's just free because you're using exactly the same stuff you used the previous frame. Now, I'm not saying that every single part of a scene can be done in this way, because obviously when you have more dynamic data, when you have meshes, when you have more complex animation, this does work with animation, but to an extent, you're still going to have to re-record command buffers every frame. But there are still perhaps large, perhaps small parts of the scene where you can utilize techniques like this. And this is where Vulkan really starts to pull ahead of something like OpenGL, because this is something you can't do in OpenGL at all. You can't do this in Direct 3D at all. So to use Vulkan efficiently, what you need to do is you need to identify places in your application where you can not just rewrite against Vulkan as a one-to-one update from OpenGL or from OpenGLES, but really find those places where you can say, I've got this new API, I've got this new programming paradigm, how can I rip out parts of my application and rethink how my application actually works to take full advantage? So once you've submitted your command buffer to the GPU, Tobias is going to be talking about more like this, the driver doesn't hold your hand here. If you submit something to the GPU and then free it, reset it, most likely going to crash, probably going to lose your process. So this is just trying to show that it's entirely the application's job to manage what state a command buffer's in. And this is just a snapshot of one object, but most objects in Vulkan are the same. It's your responsibility to manage the lifetime of objects. So if you've submitted something to the GPU, don't free it. So we've got our command buffers, but what do we actually stuff in our command buffers? So the primary thing that we stuff in command buffers, compared to OpenGL, which gets us the big performance win, is pipelines. And you can have graphics pipelines or compute pipelines. Compute pipelines are basically the same, just shrunk down. So I'm going to talk about graphics pipelines because they're a little bit more interesting. So what is a pipeline? A pipeline is a whole bundle of state which is immutable. And it's the immutability which is really important compared to OpenGL. In OpenGL, you can fiddle a bit of state here, you can enable a bit of state here, and the driver just has to deal with it. So a pipeline consists of a bunch of fixed function states, which is basically everything that isn't a shader. And it doesn't specify the exact data for the pipeline, it just specifies the layout of that data. And the problem is, the dirty secret with GPUs, different depending on the implementations, but different parts of these fixed function states might not be fixed function at all. They may actually be implemented as part of the shader, which means in OpenGL, where you can enable or disable these states completely independently of changing the shader or the program, what the implementation has to do is it can't actually compile the pipeline at the point in time you asked it. It's got to wait until draw time before it sees the full amount of state available to it before it compiles that pipeline, which leads to awful hitching, unpredictability. And even if you do end up using exactly the same pipeline with exactly the same set of state every single frame, the driver doesn't know that you're doing that. There's no way to say, GL, I promise I'm not going to change anything, which means that the driver has to worst case every application, even if it's a good application. And this is something Vulkan just immediately gets rid of. Pipelines, by being immutable, means the driver doesn't have to worry that you're going to change them later. So just a brief overview, shader states, it's basically the same as OpenGL at the moment, today that is, and there's nothing special there. Same with compute. Compute has a single stage, which is the compute stage. The other thing that goes into the pipeline boiling pot to get mixed in is the descriptor layout. And this is, again, where we kind of differ from OpenGL. OpenGL says there are 16 textures and 16 buffers, and any shader can use them in whatever combination they want. The problem with that is the driver doesn't want you to do that. It doesn't really want you to use image 0 and image 15 and nothing in the middle because it doesn't know. So at draw time, again, it's going to do some optimization for you, which you might not want because you might be a good application. So in Vulkan, we just say, again, don't make the driver have to guess. Provide more information up front. So the descriptor set layout is a way of you telling the driver exactly what type of resources you're going to use and in what way. Again, it's not the actual resources themselves. Of course, you can use the same pipeline with a different set of buffers, as long as those buffers are the same layout. And finally, although I said pipelines are completely immutable, they're not actually completely immutable, because I think as application developers, you'll be somewhat upset with us if we said you couldn't change the scissor or the viewport every single time you banned the pipeline. You would have to compile a new pipeline just for a screen size, which would be insane. So there is a little bit of dynamic state that you can set, and this is set independently of the pipeline. However, again, in the spirit of telling the driver things up front, you can't just use dynamic straight away. When you compile the pipeline, you have to tell the driver, I am going to be changing this state dynamically. And you shouldn't just set everything to be, I've seen applications that do this, you shouldn't just set everything, I'm going to use it dynamically, even when you're not going to use it dynamically. If state isn't set dynamically, there's still space for an implementation to optimize that pipeline. So really only use dynamic state when you need to, and the set of dynamic state that you need to use will differ from application to application and probably differ from pipeline to pipeline. The final part of the pipeline story is the pipeline cache. So what's very interesting, what I find at least very interesting, is our Vulkan implementations aren't going to hold your hand. We're not going to do anything for you. And you can do an experiment, which is in OpenGL, get a bunch of shaders called GL shader source, GL link program, etc., and time how long that takes, and you'll get a time. Go do the same in Vulkan, VK create graphics pipelines. Vulkan's going to be significantly slower than OpenGL, but I just told you Vulkan's a really efficient API. That's because GL drivers lie to you. Again, they might not be able to compile that shader at the point in time you ask them to compile it. They might have to wait until draw time. They might compile a less optimized version and spawn a thread which is going to go and rubbish your caches up, which are your application caches. But we're going to go and compile a thread because it's an arms race of who can get the fastest compile time, even though we're not actually doing any compile times. In Vulkan, if you ask us compile exactly the same pipeline 1,000 times and you don't provide a pipeline cache, that implementation will go off and do the work 1,000 times. We're not going to pretend to do work when we're not doing work. We will do the work when you ask for it, which is a good thing because it means that we're not hiding where we're using your CPU cycles, because after all, you're the application, you get to decide the distribution of those CPU cycles. So we're going to do work when you ask us to do it, which makes it a lot less guesswork from the application's point of view when stuff's happening. On the other hand, often implementations can share state between multiple pipeline compiles, which is why we have this explicit pipeline cache. A pipeline cache is a signal from the application to the implementation to say, I think a bunch of these shaders are kind of similar, so merge all the similar state together and, again, amortize the cost of resource allocation, compilation, hashing, etc., between a whole bunch of different pipelines. And the pipeline cache is also a method by which you can serialize and deserialize your pipelines, which comes back to the point. OpenGL is really fast at compiling, but when you use GL shader binary, GL program binary, what you save to disk is often not the actual hardware code. You're saving off some hardware code, some metadata, because again, the implementation can't actually compile the program just based on the data that you've provided it in the shader. In Vulkan, because we can compile everything up front, everything gets baked into that pipeline. When you do a pipeline save off to disk, we actually save it off to disk. When you load it back in, you load everything back in. There's no more runtime compilation. So if you can run primarily from a pipeline cache, you'll never pay the cost of pipeline compilation on subsequent runs. So these are just two ways in which Vulkan really gives you that performance. And it's not just performance, it's about predictability. And it's not just about CPU performance and CPU predictability. It's about GPU performance as well. If you can reuse your command buffers from frame to frame, you can get better GPU cache behavior. There are other ways in which Vulkan allows you to get better GPU performance. So natively, we support multiple queues, which allows for things like asynchronous technique, asynchronous compute, asynchronous transfers, asynchronous render commands, which allows you to exploit concurrency on the GPU as well as the CPU. Tobias is going to be talking about how fine-grained the synchronization model is in Vulkan compared to OpenGL, which again allows you to exploit more concurrency on the GPU. And I didn't really get to talk about render passes, and I think Alon might be talking about them later. Cort's going to be talking about render passes. He's not. Alon might. Tobias is going to talk about render passes. Great. I knew someone was, but I couldn't remember who. It's very early in the morning. So render passes are another technique which are primarily aimed at getting more GPU performance rather than CPU performance. So while it's strictly true that Vulkan, when imagined, was a way to get better CPU performance, it was a way to reclaim your application CPU cycles. Again, going forwards, we're going to see more and more techniques introduced to Vulkan that allow you to get better GPU performance as well as better CPU performance. So let's revisit that first slide. In the real world today, can we answer the question of when and why you should use Vulkan? Well, when should you use it? You should use it as soon as you think that you're ready to dive into Vulkan. And the sooner the better, but at the same time, getting started with Vulkan is getting easier every day. The tools are maturing and the implementations are maturing. The support is growing ever wider. And why should you do that? Well, you're going to hear over the course of today how awesome it is, and it is still pretty dope. So use Vulkan all the time. Thank you.
My name is Cort Stratton. I'm from the Google DevU VR team. I was told by many people coming into the room they didn't recognize me until I did this. Hello, I'm Cort Stratton from the Google DevU team. It's like Clark Kent's glasses. Like, oh, where'd he go? Oh, there he is. I spent the last year or so working on Vulkan on Android in the VR domain, and my team was very eager to learn about Vulkan given the extremely high performance demands of VR, but Vulkan also has this notoriously high barrier to entry, so they weren't sure. They wanted to know what sorts of benefits they could expect before they took the leap into integrating it. So I set up a simple synthetic performance test to compare our OpenGL ES code and Vulkan, and I wanted to share the results with you today. Before I go on, though, I wanted a big disclaimer. This is only one test on one device, one driver version. The Google lawyers won't even let me tell you which device, but it's a Daydream-capable phone. So my goal here is not to make broad performance guarantees about Vulkan or Android or anything specific. Please test your own code to do your own benchmarks, but it's an interesting data point, and it will give you some idea of what to expect. So with that out of the way, the test here, it's just a big old 10 by 10 by 10 room full of spinning things. You can see a screenshot here. Please don't hire me as your art director. The mesh complexity is shown on the slide. Each of these is sort of spinning around. It's a dynamic scene. You can look around. The vertex shader is a couple of matrix multiplies. The fragment shader is a couple of texture fetches with bilinear filtering. These shaders were chosen to be more or less representative of what a typical mobile game might be doing. Not your fanciest objects, but enough to get a dynamic 3D object into the world. The data for all these meshes is completely unique. So every mesh has its own vertex buffer, its own index buffer, its own shader, its own textures, its own pipeline state, its own uniform buffers. Aside from the uniform buffer, the actual contents of all those resources could be totally different, but they are in fact exactly the same because, again, I'm not an artist and I was low on time. But imagine all these things being totally different for a very rich, complex scene. The renderer is intentionally not very smart at all. It's not doing any high-level optimizations like culling or multi-view because I figured those sorts of things would impact both APIs more or less equivalently, and I was interested in like a relative performance gain, not an absolute performance measure. So instead, I'm just iterating through all these meshes, setting their state and drawing them, moving on to the next one, and then because it's VR, do all that again for the second I. And I'm sweeping the mesh count up from 5 meshes to 500 and sampling some timers and averaging over several frames and graphing the results. So, results. Here is OpenGL. So for this first test, again, I'm just setting render state and drawing for every draw call. So new textures, new meshes, new shaders, new everything between us. So there's no sharing between draw calls here. So this let me measure the worst case draw call throughput in both APIs. The solid blue line there is CPU time. The dashed line is GPU time. Horizontal axis is draw calls per eye. Vertical axis is milliseconds. Anything else to see here? Oh, I guess what I'm measuring here is purely the render workload. So there's nothing here about display sync or swap chain image acquisition or the non-graphics parts of your application. This is just measuring draw call performance. Whoops, I went too far ahead there. Okay, so here's what happens if we add Vulkan in the mix. So a couple things, it's the red lines, same scheme here. And a couple things stand out. First of all, the GPU time didn't change that much. It got a little worse in this test, in fact. That's due to a driver bug that was long since found and fixed, but I haven't rerun the data. But that's to be expected. We didn't really expect, in this case, the GPU to get much faster. But huge improvement on the CPU time. I'm doing it again. Huge performance on the CPU improvements. It's about 3 to 1. And I can't seem to, here we go. Right, so this surprised me, actually. I was thinking I would have to work a little harder to beat OpenGL so badly. But it turns out, without doing really anything clever and just doing the same work in both APIs, Vulkan was still much faster. But this is the worst case for a renderer. Let's look at the best case, which you've already seen a peek of because I skipped ahead. So in this variation, I'm only changing the state once per eye, aside from the uniform buffers that are changing every mesh to put them in the scene. So now all the draws are using the exact same textures, shaders, whatever. So there's no more binding between draws. This was meant to simulate a bindless style setup where you're binding everything up front and then doing all your draws. So note visually, this is still the exact same scene because in my case, all the meshes had the same data anyway. So visually, it didn't change. But timing's got much better. So the GPU time improved in both cases due to better cache utilization, but still pretty similar except for the constant offset, which I mentioned. And the CPU time still got much better. It's still about the same gap. So the conclusion here for me was that in a fair fight, the pure rendering work of both APIs, it's about a 3 to 1 gain in a fair fight between Vulkan and GL. But as Michael mentioned, we don't need to fight fair in Vulkan because Vulkan can do things that GL can't, like record command buffers. And so if you do that, as expected, that's the yellow line coming in here, your CPU time effectively becomes a constant, and a very low constant at that. The GPU time doesn't really change because it's the same command buffers again, either way. And again, I want to emphasize that visually, this is the exact same scene in all 3 cases. It's still interactive, still dynamic. There's a misconception I've seen a bunch that recording a command buffer and replaying it means rendering the exact same pixels. That's not the case. It just means making the exact same draw calls and bindings in the same order. So there's a lot more flexibility there than you might think at first. So these were good numbers. And in conclusion, I have no conclusion. I don't have time for questions, and I'm flying back home before the Q&A panel. But come find me at lunch, and you're in good hands with the other presenters. They can answer your questions. So thank you.
My name is Mark Young. I work for LunarG. Probably most of you don't recognize me because I'm not one of these really smart guys who've worked on Vulkan for years. I have taken over the Vulkan loader, and our company works on the loader and other tools, as well as the SDK, with a lot of funding by Valve, actually. So before you begin, I want to cover some of the basic things that you need. Obviously, you need an operating system. Right now, the main ones are Windows 7 or newer, basically a Linux distro that's at least a couple years old or newer, C++ compiler, ideally one that supports C++ 11 features, because a lot of our layers and tools rely on some of those features, and additional tools like Python, Git, CMake. One thing that you'll probably notice, there's no Apple support. Right now, Apple is sticking with their metal layer. However, there is a utility going on, a project going on to try to bring Vulkan on top of metal, and that's called Molten VK. So if you're interested in trying to get Vulkan support on Apple at all, that's an opportunity for you. So I'm not going to cover this in too much depth, but as I mentioned before, there's a lot of support out there. Valve, in its current hardware survey, as I said, roughly about 50% of the desktop items can support Vulkan in some extent. Here's a list. Well, that didn't come over very well. One thing I would like to mention is that for Android, you will need a NuGet device, and if your NuGet device does not support Vulkan, it'll actually return 0 hardware devices whenever you try to run an application. So be aware of that whenever you do try to write for NuGet. So I'd like to first talk about the SDK. Why would you want to download the SDK? So there's actually 2 SDKs, but each one contains useful tools, including the most recent spec changes. Each week, roughly, the team comes out with a new Vulkan spec, which includes newer extensions, updates to language, bug fixes, that kind of thing. So if you want the best and most accurate spec, get the latest one. The SDKs also come with validation layers, which we spend a lot of time on. Right now, roughly about 80% of the spec is covered by validation layers. So if you try to run something, as we'll cover in a few minutes, 80% of the errors in the spec will be caught by the validation layers. And some of them in a way that make it pretty obvious what you've done wrong. Obviously, we also include some samples and some other tools. So first, obviously, there's an Android SDK. It's put out there by Google. There's a link. Again, these slides will be available for download later, so I'm not going to cover them in too much detail. And then we have a separate SDK for desktop, which targets Windows and Linux. And the additional thing about the desktop SDK is we include what's called the Vulkan loader as part of that, and additional layers that you can take advantage of that aren't in like the Android SDK. Now, one of the goals we try to do is we try to release a new SDK every 4 to 6 weeks. And that's because it includes newer changes to the validation layer, newer spec changes, and everything else. So especially if you're actively working on an application, we recommend that you go check and download the latest. In fact, if you sign up for our MailChimp, we'll send out an email whenever the newer ones come out. One of the first tools I want to talk about is a Vulkan installation analyzer. And I don't know about you, but one of the first experiences I had with Vulkan was I would put stuff on my machine and all of a sudden, hey, nothing worked. And one of the items that we wanted to do was to provide a tool that you could use that would run and generate some kind of output that would say, hey, what's wrong with my system? One of the other things we've ended up using this for is before you file a bug, it generates an HTML that you can supply back to someone. And if you're an application vendor, maybe you want to receive these yourself from a customer. And that's going to include a lot of the system state that you have on your system. So for example, on this slide, you'll see that here are some of the example command line outputs. It's very simple. It's just a one line, so it'll say something along the lines of, hey, everything worked, or hey, you're missing a driver. Again, you have the HTML here. Each of these sections that you see in gray are collapsible sections. They include information about your Vulkan environment, as well as what SDKs, what runtimes it finds, what layers are available, information that you can find useful in debugging a situation. Now, I want to talk about the Vulkan loader. As these guys have mentioned, one of the big draws to Vulkan is that it tries to step out of your way as much as possible. And that's true for the loader. So the Vulkan loader is kind of the gateway to the Vulkan on your system. It's similar, if any of you have dealt with Windows especially, to the OpenGL loader that's on Windows. Unlike that loader, which is controlled by Microsoft and is updated very infrequently, this is controlled by Khronos. It's updated roughly every 4 to 6 weeks. Actually, it's open source too, so if you want to go get the source and build it yourself, it's updated daily because we're actively working on it. And again, the only requirement if you want to submit code to this is a CLA, and it's Apache 2. You feel free to contribute code all you want. We'll take whatever you've got. Now, it gets the runtime in the loader is installed on your system anytime you install a driver from certain vendors, so like NVIDIA or Intel. It's also installed with applications, so if you install some of the Steam games that use Vulkan support, it's installed with that. And finally, it's installed with SDKs. And it's supported so that you can have multiple loaders installed simultaneously. It's going to use the newest and greatest. This is roughly what the loader looks like from a high-level standpoint. You can see on the left is all your Vulkan applications. It's going to interface with the loader, and the loader is going to find the time when it first gets a couple of calls to go find all the available layers in the system. It'll also find all the available ICDs in the system. And then once you start using those, it'll enumerate all the physical devices that you can use on your system. So it's responsible with controlling all this and revealing this information to your application. So I've said loader, but there's really loaders. There's two. There's an Android loader and there's a desktop loader. And obviously the Android loader is closed source, but the desktop loader is open source. But Google and LunarG have made a concerted effort that we design one interface. And that interface is actually on the GitHub, and I have a link at the end. So if you want to know how the loader talks to an ICD, if you want to know how a loader talks or works with a layer, it's all in that document, and it's all the work is done together with the Android team to try to make sure that the interface to you guys remains the same. So one of the high-level concepts we want to cover in the loader is that there's two different groups that Vulkan objects deal with, and that's an instance level and a device level. In this case, what you're seeing is an instance. The instance has to work with every single ICD and physical device on a system, because at any point going forward, you could start working with any of those devices. So if you have an instance item, it has to talk to everything. On the other hand, if you have a device, you know specifically which physical device you're working with. And so the loader has to worry about those two different kinds of calls. Excuse me. And the reason why is each object you create in Vulkan is dispatchable. That means that when you create something, and inside of that object structure, it contains a dispatch table to know where it needs to go throughout the entire call. As you can see in the first call here, I've got a display. We got a VK get event status, and the very first item in the list is a VK device, and that's a dispatchable object. Only 3 commands don't take dispatchable objects. I can tell you them if you're interested, but for the most case, you don't really need to worry about that. Again, this is just a quick diagram showing a dispatch table, pointer being the first thing. So this is why you need to know. And oops. It's because of the way that your call is going to look whenever you call a function in Vulkan. So the first call here is an instance call chain. And so for any instance command, your application, no matter what, is going to trigger the loader first. It's going to go through any layers that are available that you have enabled as part of your instance. Then it's going to enter the loader again to be distributed to all available ICDs. Because a device already knows where it's going, we can actually remove that terminator, and so your device call is a little more optimized. This is going through the loader exports of a device function. If, in some cases, you want to write your own dispatch table in the application, we can step out of the way. And what you can do is use Vulkan VK get device proc address. And so for any device function that you want for your device, if you query that, you can set up a dispatch table, and you can see the loader has completely stepped out of the way here. So if you want the most optimized call, you can set up your own dispatch table, and the loader will just, for the most part, step out of the way. There are a few cases where that's not true, because the loader has to worry about some things that it has to translate for the ICD. In one of those cases, it's the Vulkan surface. So the Vulkan surface is actually a special object that the loader has to translate. And unfortunately, anytime you use a Vulkan surface in a function, it ends up looking more like an instance chain. But that's like 3 functions, 4 functions at this point. So for the most part, you're going to get the last if you use it properly. Now, just like OpenGL, Vulkan can be extended. And there's extensions for instances and there's extensions for devices. The loader really cannot support instance extensions because, again, that terminator is on the end. So if you want to get new functionality that's an instance extension, you have to get a new loader. And so that's why we actively try to maintain updating the loader at a 4 to 6 week cadence, because we want to make sure that you guys have access to the latest instance extensions. Because there is no terminator on the loader for device extensions, you can have all the device extensions you want, and the loader will just function properly. So if you're using the loader, again, as I mentioned, it's very thin, and something happens, there is the option of just on the desktop outputting some debug information. And it's just an environmental variable. That should work on Linux or Windows. So because Vulkan is very thin, and that includes the loader, you can crash it. If you do something incorrect, like if you pass an instance object to a device call, you will crash. If you pass and if you set up, if your device has 2 physical devices on it, and one supports a whole bunch of new extensions, the other one does not support, and you set up the dispatch table for the one that supports all the extensions, but call it with the device that doesn't, it's going to crash. So it's going to give you enough rope to hang yourself. So looking for ICDs, it actually looks in different locations based on your operating system. On Windows, it's going to look at the registry, and there's a registry location right here. And on Linux, it's actually going to look in some standard folders. Again, if you want more details, you can dig into the loader and layer interface doc. If you really want to force your application to use one ICD, so if, like my laptop has an NVIDIA discrete card and an Intel integrated, one of the options is you can force, wow, that came out bad. You can force the VK driver's path to say only use this one folder that ICDs are located in. Or if you want to force the specific ICD JSON file name, you can indicate that with the second. So next we're going to talk about layers. Layers are actually a really interesting concept in Vulkan. So on OpenGL, all your validation was there all the time. Not very useful sometimes because you could just get a GL get error, but you had to do it after every single call in order to track it down properly in most cases. What Vulkan has done is they've introduced this concept of having optional libraries which you can load at runtime. These are called layers. And you can set them up from your application during VK create instance, or you can actually force them from the command line on the desktop. So if you want to force on validation to something that doesn't have validation enabled by default, you can actually use VK instance layers. So what kinds of functionality can you get from Vulkan with layers? You can obviously, like I mentioned, you can get validation. You can actually track debug data. You can record your Vulkan calls. You can log content. You can capture a screenshot. You can overlay additional rendering commands onto your screen for debug data on your application or just a simple frame rate. Layers are actually really cool, and I recommend that you at least try to write one, if nothing else, for your own debug data, as well as using the validation layers. So why should you use validation layers? Obviously to test correctness, but also because it'll help you with the portability. I don't know how many of you have done, OpenGL development on a desktop, but sometimes you'll render an application, it'll work correctly on one vendor, and something will be wrong on the next vendor. And the intent is to try to follow the spec precisely with the validation layers and give you some kind of hint that, hey, even though things are looking good, you're probably doing this wrong and you should change. as well as we also want to try to give you some hints eventually on performance and other usage. And so several vendors that we have that have given us feedback on using the layers include companies like that. So I've said standard validation a couple of times. What is standard validation? If you want to turn on validation at this point, you actually have to manually turn on each layer. So we have 7 layers here. We have a threading layer, which validates obviously threading. We have parameter validation, which checks, null pointers and various other input commands to the Vulkan commands, as well as all these other layers. I'm not going to go into too much detail. So right now, especially on Android, you have to intentionally activate each of these layers. And as we're going on in time, we're trying to add layers, we're trying to collapse layers, we're trying to add more and more validation. And so as a utility, we've created one global layer which just says turn on all the validation you want. Now this is only on desktop, unfortunately. Right now on Android, you still have to manually call out each layer in your APK whenever you want to use it. So now let's look at an example. I wrote my application, I ran it, I see no VK results that are problematic, and I get that. My first response, Vulkan sucks. If you turn on validation, however, you get this command. And you can see pretty clearly, hey, you must call end command buffer prior to calling VKQ submit. Okay, I fix that, all of a sudden, I've got my image. So it's not going to be that easy all the time, but we endeavor to try to give you as much information as you can to make it easy. And again, I just want to recover that you want to grab the latest SDK to get the best and most recent layers because we're continually improving them. So you don't want to turn on validation. This is one of the reasons it's a layer. In OpenGL, it was always there. It was always impacting your application. Because it's an optional layer, you can turn it off. If you turn on all the validation right now in one of our tests, you go from 160 frames per second down to 6. Now this application is multi-threaded, it's running a lot of draw calls, it's doing a lot of work, but you can see that you definitely don't want to try to accidentally ship with validation layers enabled. Sometimes, though, you might want to turn on validation layers for your application, and it's still going to suck. It's still going to hit that 2-3% threshold of your full performance. What you can do is you can turn off some of those layers that we mentioned before. Those 7 layers, you could just manually enable those manually, and then say, hey, I don't need threading this time because I know I'm thread safe, or something like that. And it'll bring up your performance depending on what you disable. So as I mentioned during call chains, each command has to worry about where it's going. If you implement a layer, unfortunately, you don't really have access to those dispatch tables that are internal to the objects. We do have utility functions you can use if you write a layer and you want to create your own dispatch. We do have some extensions in there, but not all of them. Again, whenever we write the layers, typically when we release whatever was available at the time, we'll try to have in the dispatch table utilities that are available to you. One of the interesting things if you do write a layer is you do not have to intercept every single call. You only have to intercept what you want. So every single layer, because of the way it interfaces with the loader, has to at least define create instance, enumerate instance layer properties, and get instance proc address. That opens it up for anything, intercepting anything in the instance call chain. If you want to intercept any device commands, you also have to interface with these. But once you do that, again, you can see all kinds of combinations here for both the instance and device chains. Just like the ICD files, the information for layers on desktop is actually stored in JSON manifest files. Those files can be found in the given locations. What's nice about using the manifest files from the loader standpoint is we don't actually have to touch a library until you tell us to. And that's for security reasons. We can read the manifest file, pass along the information to you, and if you don't want to load the layer, you don't have to. And we have a couple of environmental variables there. If you want to force on, again, any layer, you just pass in a delimited name list of the layers you want to enable into instance lists. And if you want to force a different layer path than what's going to be loaded by default, you can use that environment variable. And again, the second one is also comma delimited, or sorry, not comma, delimited based on your operating system, so colon or semicolon. And that's useful if you have multiple layers and multiple paths. You can pass in all the layers there, or the paths there, excuse me. Okay, so what about desktop? It's not that easy again. There's this concept of implicit layers on the desktop, and implicit layers are always there. One example of an implicit layer is NVIDIA Optimus. So I don't know how many of you, again, have laptops with an NVIDIA discrete card and an Intel integrated, but the Optimus layer sits there and actually reorders. So if you're unplugged and you're running on battery, it'll shift the Intel graphics card first. If you're plugged in, obviously you're going to want best performance, so it's going to shift the NVIDIA card first. And so that's always there. It can be disabled. Every implicit layer that is defined on your system requires that an environment variable is available that can be used to disable that layer. And if you run VIA, actually, it'll capture your system state and tell you what implicit layers are there and what environmental variables you can use to disable it. And then every other layer that's available is called explicit because you intentionally have to enable those. This is not on Android. There's only explicit layers on Android. So if you look at the loader, and at the bottom you can see we separate the layers into the three groups. So if you define an implicit layer, it's going to be loaded in the first part of your stack. If you have environmental variables used like VK instance layers, it's going to be loaded next. And finally, anything the application enables will be loaded. One warning that we have, if you do define a layer, is this idea of wrapping. And the idea of wrapping is if during create device, let's say, on the way down you pass the create device, on the way back up you say, hey, I have my own object data that I want to track with a device. So instead of returning the lower down created device, you pass back your own object. That can cause problems. And the main problems is that you must unwrap your device going forward for any function that ever gets defined that uses that object, in this case a VK device. Any extension command, if you want to properly interact, because remember, your layer only has to intercept what it wants to, but if it doesn't know about a new command, you're passing now the wrong object pointer down to the next layer. It's going to crash. And so if you wrap something, it can cause problems. There are some suggestions that we have done personally because we have to wrap. And in those cases, we have a whitelist of extensions that we work with. And so if we see something we don't know, we throw up a warning, hey, we don't know what's going on here. It might cause problems, and it could be because of that. A better alternative, honestly, is if you can, use a hash map lookup using the return values. And that way, if whatever you intercept, you can look up the data in a separate area and then go on your merry way. And if you don't intercept every single command that touches that device or that object that you created, it doesn't matter. Hey, one of the last tools I want to talk about is RenderDoc. And RenderDoc is a graphical debugger that does have Vulkan support. Unfortunately, right now it's only on Windows, but it's really a useful tool if you want to use it to investigate what's going on with your Vulkan application. We actually install it as part of our Windows SDK, but you can get it on GitHub as well. So here's an example screenshot. What you can see here is on the left is all the Vulkan commands that are being passed down. You can see they highlighted a mesh as well as having texture data. So it's a very useful tool. Unfortunately, it does not have any of the GPU internal data. So you don't have throughput numbers, you don't have dropped pixels, called pixels, or anything like that. So it's a good start to get you some of the information you may be wondering about Vulkan, but if you really want detailed data and going the next step, you will have to use your hardware-provided tools. But I have found that it's a very good tool, and I would recommend that if any of you are interested, at least take one of the demos that comes with the SDK, go and capture a frame of cube, let's say, and just step through the render doc and see how it is useful to you. It's written by one of the really sharp guy, Balder, who now works at Valve. And obviously there's other resources you can do. Graham Sellers worked on the Vulkan programming book. And I think also John helped out too. So one of the speakers that we have here today will be talking to you. There's also a Vulkan tutorial. If you want some step-by-step language, the SDK as well as on our website, LunarG, has information on how to step-by-step go through Vulkan. If you want some really cool demos, tessellation, other things like that, Sasha Williams has some really great demos if you get to the more advanced topics of Vulkan. And there's many others. I know that Khronos has a website dedicated to trying to keep up-to-date resources on there for demos, tutorials, anything else. So always check back and see if there's anything of interest to you there. And finally, I just wanted to give a list of links in case that may be hard to read, but you'll all receive a copy of the slides, I believe. So everything's out there. Molten VK and RenderDoc are at the bottom. And as I mentioned, that the loader layer interface is also on GitHub. So please feel free to contribute bug fixes or any other thing. And thank you very much. Any questions? Okay.
Don't go too far away, Mark. So we're in real good shape as far as time goes. So if you have questions for Mark or for Michael or myself, and Cort is still here. Shoot. I realize we've covered a lot of material ranging from the fluffy philosophy to design. Yes?
Extensions on the instance, does it automatically apply to the device or vice versa?
So
We do have to repeat the question because we got video and it's not going to pick up what you said.
So let me just try to rephrase it. So you're wondering if you have instance extensions, do they affect the device or device extensions, or I'm sorry, can you repeat that?
So you have the debug layer that you apply on the instance. It seemed like from your slides that you were just applying it on the instance, and then it would give you information on the debug output. Do you also need to apply it on the device as well?
So that actually, it's a really good question because originally when they designed Vulkan, you could enable layers separately per instance or per device. The concept of device layers kind of just went away at some point. So if you enable layers at an instance level, they're enabled for everything under that instance, including any devices you create as part of that instance. So if you need the debugging or the validation, just create it for your one instance and then it'll be there for everything else. Yeah, so the question was, have the device layers been deprecated? And they have. So if you look at the very early versions of the spec, it'll talk about device layers being separate from instance layers. That's no longer true. They're the same exact thing. And if you try to do anything with the device layers, it's actually deprecated and it's pretty much ignored. Just out of curiosity, how many people here have actually used validation or Vulkan applications yet? Okay. If we actually, just to point out, we have a gentleman back there on the far right who's done a lot of the validation layer work. He's hiding back there behind his laptop. But he will be here available after the session's done to answer some of your questions, if you have specific validation layer questions.
Just a question regarding the direction that Vulkan's heading, because I know one of the big problems we had with OpenGL, which you sort of touched on, was the cruft that you had as versions went on. With Vulkan, are we planning on providing backwards support for all versions of Vulkan previously, or are we going to do follow sort of what the DirectX model is, where you just drop it?
So it's always a challenge, when we come out with a new API, we don't know what the uptake's going to be, and we don't know when is an appropriate time. We do intend to be quite religious about minor versions, so a 1.1 should run all 1.0 code. We do intend that when we make a major rev break, it will be a compatibility break, and we will feel free at that point to drop stuff. We are still wrestling with the question as we look at our next version, how are we going to handle things like extension compatibility? So we've had, as you know, in OpenGL, an extension gets defined against version 2.0, and then people still ship it against 2.1 and 3.0, but it isn't actually defined against it. And if you read the spec, you discover, gee, that doesn't always entirely make sense. With Vulkan, and it's purely because of the tools, because we express an extension as a merge request against the spec, it is not possible for when we have an extension against 1.0 and we move to 1.1, if it doesn't merge clean, it's, we know we have a problem, and we will maintain those, we think. It's going to be, it's a learning experience for us to operate in this way. But the commitment from us is we expect to rev more often than GL did in terms of major releases, but we don't have a particular target for when it's the right time. And we do intend to be extremely clear about, we're not going to go to a major rev just because it's a nice marketing story. When we do a major rev like a 2.0, it means compatibility break.
I actually have a question for Cort, if possible. Just going back to your performance slides, you mentioned very briefly bindless modes, and I was wondering if you thought that bindless was a good approach for Android specifically.
I don't have a great answer for that yet. The device I was working on did not support the necessary features for full-on bindless, but I am optimistic that it is a good idea, although it doesn't make as much of a difference in Vulkan because the bindings are so much cheaper anyway that, yeah. So that's my hope, but check back in a while and I'll hopefully have a better answer.
Yeah, there is no, at least official Khronos extension for like bindless textures such as NVIDIA ships. I don't know if they have a proprietary extension. I don't even track what they're shipping. No, Marcus says the answer is no. Yeah, I mean, bindless is an interesting idea. It requires some hardware capabilities that not all hardware can do. So actually, this is quite, if you're a spec guy, it's kind of interesting. Maybe not if you're not. But as I think you all know, the first draft of Vulkan was Mantle. And Mantle was a lovely API, very efficient, did certain things very well, quite specific to the hardware that it was designed to run on. And a lot of the work we did in the first year was abstracting away all of the hardware-specific stuff and finding a model, an abstraction, which all of the devices out there could support with roughly equivalent smoothness. So bindless, not an option for us because there's enough Vulkan hardware out there that can't do it. We probably will eventually go that way because long term it's pretty nice. Now Michael's going to argue with me. This is good. This is why we have.
No.
Go ahead.
I think, well, the discussion we had, I'm going to try and not be biased, was that the model we have with the descriptor tables is actually most of the way towards bindless anyway. The thing you do get is this idea of being able to bind everything up front and say, these are all my resources up front at the start of my frame or at the start of whatever, and just use them. So that sort of is there. There's no individual bindings as such in Vulkan compared to GL, which actually gets you most of the performance that you would get from bindless anyway. With that in place, we didn't find too much need to do bindless. One thing bindless does do is that because you don't have the bindings up front in any way, is it's an extra indirection. So some hardware vendors are not keen on this extra indirection. So the table model makes a lot of sense. We are looking at ways to improve things to make it so that you've got more of what bindless has. One thing some of us have looked at is the idea of being able to update your descriptor tables more in other ways. But we haven't finalized on anything yet. But yeah, I'm not sure that there would be broad support for bindless, at least not now. But there may be broad support for things that get you closer to that.